Hello, everybody. I'm Dr. Ahmed Amin Nasser, your biology educator, and today I'm going to talk to you about biological molecules, carbohydrates. Now, look there. Where can we find biological molecules or life molecules? Just focus, or even better, zoom in. Here we go. This is the old good sun with its 9 children. One of these 9 children is live and kicking. So let us go down to earth and see the sun energy perfusing everything. Here we go. The solar energy through photosynthesis will unite carbon dioxide and water in order to produce glucose and oxygen. Glucose is the cornerstone of energy molecules in our entire life on earth. So, once we attach sunshine to air and water, sweetness comes out of that. Not only sweetness, sweetness and energy and life. So the sweet sugar, glucose, is our body's energy source. What is it formed of? Well, it's formed of carbon, hydrogen, and oxygen. We earlier agreed that it's carbon dioxide and water, so it will come down to carbon, hydrogen, and oxygen. And the carbon will be 6 carbon atoms, to which oxygen atoms, 6 oxygen atoms are attached to it, and then finally 12 hydrogen atoms are attached around in order to satisfy the 4 valence of carbon atoms. Because of chirality, we would have more than stereoisomers, more than one, a lot of stereoisomers. Actually, it depends on how many chiral centers we have. So let's see here, we can find that C2, 3, 4, and 5 carbons are chiral centers. So we will have 2 to the power 4 stereoisomers, or 16 hexoses, 16 sugar, which is formed of 6 carbon atoms. However, life has struck a deal with dextrose sugar, not L sugar. So D-glucose and D-galactose are the main 2 components of these 16 hexoses. Not only that, but also we have to note here that these hexoses could be straight or cyclical. Most of the time would be cyclical, especially when it comes into compounds. And we have 2 isomers here, alpha and beta, or alpha anomer and beta anomer, depending on the presence of anomeric carbon atoms. So we have one anomeric carbon atom, where it's alpha, you will have the OH below OH of carbon 1, below the ring structure, below the level of the plane of the ring structure, or on the other side of CH2OH. And beta glucose, or beta anomeric glucose, where you have the OH above the plane of the ring or towards the same side of CH2OH. And it happens that because of the structure of alpha, it's easily burned into production of energy. However, the beta structure, because of its presence on the same side, OH and CH2OH, so that will help in structuring or stacking these molecules in order to bring about strong structures. Glucose and galactose are not the only sugars that are present in nature. A very important 6-carbon sugar as well, called fructose or fruit sugar, make the triad or the trio of fructose, glucose, and galactose. These are the three musketeers which are going to carry on building up more and more complicated carbohydrates. Now, monosaccharides of carbohydrates, as we agreed upon, it's almost hydrated carbon, as the name implies. So it's CM H2O between brackets by N molecules. M and N are the number of the atoms. M is the number of carbon atoms, and N is the number of H2O molecules. However, there are certain sugars which do not comply with the C and H2O, and that is deoxyribose of DNA or ribose of RNA. So monosaccharides, which is carbon, hydrogen, and oxygen, it depends on how many carbons are there, and that would give different function of their molecule. So if there are 3 carbon atoms, it will be triose, O's as sugar, triose, tetrose, if it is 4, pentose, where it is 5 carbon atoms, and of course hexose when it is 6 carbon atoms. So these are the monosaccharides, or the building blocks of carbohydrates. Now, these are sugars and they are sweet. All of these are sweet because they can fit into the sweet center or sweet site over the tongue, stimulating it, making the brain receive its sweetness. When these small blocks attach to each other, more complicated compounds of carbohydrates are produced. So the first step is that union of 2 monosaccharides, and the commonest of that is sucrose, which is formed by alpha glucose, or rather alpha D glucose, and beta or beta D fructose. When you have these 2 molecules combined to each other, you lose 1 molecule of water. So sucrose, as we said, it's a disaccharide, or 2 monosaccharides combined to each other, glucose and fructose, and you can find that in table sugar and plants. Lactose is formed of galactose and glucose. You find that in milk. Maltose, which is formed of 2 glucose molecules, and you can find that in any more complicated saccharides, which is going to be broken down, and also in malt sugar. Monosaccharides and disaccharides, with exception of sucrose, are reducing sugar. they donate electrons or hydrogen to compounds, so they reduce the compounds and they are going to be oxidized. And that's how we check over its presence, by having Benedict's reagent heated with the dissolved sugar for some time, and the color will be changing. And it's also semi-quantitative, so according to the color you might expect how much, or you might estimate how much sugar is there. Sucrose is not reducing sugar, though it is formed of two reducing monosaccharides. And I'm going to ask you to look it up to see how comes sucrose is not reducing one, and concentrate on the anomeric carbon molecule, which is not free in sucrose to be able to reduce other compounds. So we start with monosaccharides and then disaccharides, and then if the monosaccharides are combined in a number from 3 to 10, this is called oligosaccharides. So oligosaccharides, you have very good function for that, very important function for that. First function of it is cell recognition and cell binding. It's either glycolipid, where the sugar residue is attached to a lipid residue on the cell membrane, or glycoprotein, where the carbohydrates residue or moiety is attached to a protein molecule through the cell membrane. And all cells are coated in either glycoproteins or glycolipids, and this will add to the cell recognition, cell identity. And this is very obvious in cases of blood grouping, ABO. The glycolipids actually is the main, or the key structure which differentiate between a red blood cells grouping A, B, C, or O. And also glycoprotein, it's very important to identify the cells or to bind these cells with something else. So in immune response or inflammatory response, this glycoprotein will play a very major role. So oligosaccharides gives cell identity and cell adhesion on one side. On the other side, not all the oligosaccharides has got that function. Some oligosaccharides are just storing monosaccharides, like raffinose in plant tissue, which is just the three molecules, the three musketeers together in one molecule, galactose, glucose, and fructose, which is kind of a store or an energy store in plants. Now, it's impossible to use all the time small monosaccharides or oligosaccharides. We need it in order to live longer. We need it to store, to be able to concentrate these monosaccharides into a bigger structures. And here we go, polysaccharides are far and far bigger than monosaccharides and oligosaccharides. Now, we said oligosaccharides from 3 to 10. I don't like you to have the impression that polysaccharides from 10 to something. No, it's more than 10. However, it's always in the thousands of molecules. So starch, which are polysaccharides of glucose, In plant, glucose is attached to another glucose at alpha 1 4, which will lead to amylose non-branching. However, if it is attached at carbon 6, then it might cause another branch, and then it will become alpha 1 4, and again at certain stage after 20 units of alpha glucose, it will be attached at 6 carbon, to be alpha 1 6, and again and again and again. So you will have branched amylopectin. So starch is either helical amylose or branched amylopectin. Polysaccharides in animals are called glycogen. And glycogen is just kind of a 30,000 glucose monomers. And again, it is highly branched. So it's alpha 1 4 and alpha 1 6 glucose after each 10 monosaccharides units. And this glycogen uh, stores these glycogen stores energy in liver and muscles. Another type of polysaccharides, which is made from beta glucose, and we said that beta glucose is very adaptable to structure formation, and you can see they are stacking in layers over each others with hydrogen bonds in between each layer horizontally. That makes the structure very strong and gives the shape of the cell wall and plant, of overall shape of the plant. And also in some other kingdoms, like in fungi or arthropods, it makes the exoskeletons of arthropods, like in spider and crustaceans. Now, these polysaccharides are insoluble. Of course, you need to store this glucose, so it has to be insoluble, and also it is taking less space, so you can store more and more energy. We as human beings cannot digest the beta glucose. Even cows cannot digest beta glucose on their own. However, ruminant animals like cattle, deer, and their relatives, they have forgot where symbiotic bacteria can work on these beta glucose bonds and destroy it or metabolize it into smaller monosaccharides, into glucose. So this is the only way of digesting these cellulose structures. However, in humans, we cannot do that, and we don't have these bacteria. So all what this cellulose is doing for us is supplying us with fibers, which has got certain good function. Later on, we'll talk about that. So in summary now, polysaccharides in animal kingdom, it's glycogen, and this glycogen is very branching or highly branching, storing energy in liver and muscles. In plant kingdom, it's either energy or structure, and the energy will be amylose, which is helical, or amylopectin branching, and also cellulose for structure. And you can see that they are stacking above each others in a very nice way, which adds strength to the structure. So carbohydrates supplies us with energy, energy for life, not only energy, structure in certain kingdoms, including plant and crustaceans, cell identifications and binding, and also it is a component of especially pentoses are component of DNA, RNA, and ATP. Thank you.